Hey, it's Jay, and today we're going to talk about the molecular basis for muscle contraction. We know we have to move to stay alive, and muscle is a motor that allows us to move. Muscle takes the energy from food, turns it into ATP, and then uses ATP to generate force and motion. In the last few videos, we talked about how a nerve causes an action potential, and then that electrical signal will trigger the release of calcium from the sarcoplasmic reticulum. The goal today is to talk about how that calcium leads to the generation of force. By the end of this video, you should be able to describe how the little molecular motors in the sarcomere burn ATP to make us move. We'll start with the muscle fiber and the action potential that spreads across the sarcolemma and down the T-tubules. This causes calcium to be released from the sarcoplasmic reticulum, so calcium is surrounding each of the myofibrils. Each myofibril is a string of sarcomeres, and we'll zoom in on a sarcomere to see how calcium changes things. The sarcomere has two edges called Z-lines. Between the Z-lines are thick and thin filaments. The thick filaments are made of myosin, which is a motor protein that uses ATP to do work. The proteins are stuck together at their tails to generate the filament, but the heads are free to bend ATP and grab the thin filament. An important structural feature of the thick filaments is that myosin on each half of the sarcomere is oriented in the opposite direction. This means that myosin on the right half of the sarcomere can pull the Z-line to the left, and myosin on the left half of the sarcomere can pull the Z-line to the right. The thick filaments are connected at the center of the sarcomere, called the M-line. The thin filaments are connected to the Z-lines at the end of the sarcomere. The thin filaments have three proteins: actin, tropomyosin, and troponin. We'll start by drawing an individual thin filament with a lot of actin proteins. Each actin protein is globular, and it has its own myosin binding site. In a cell, the actin monomers assemble into a double-stranded filament that myosin can bind in a lot of different places. The next protein is tropomyosin. At rest, tropomyosin covers the myosin binding sites, so myosin can't grab the thin filament. Troponin is attached to tropomyosin, and it binds calcium with high affinity. If calcium is around, it will bind to troponin. Troponin and tropomyosin are called regulatory proteins because they control whether or not myosin can bind to actin, but they're not necessary for muscle contraction. When calcium binds to troponin, it causes troponin to change shape. Then troponin pulls tropomyosin away from the myosin binding sites on actin. This allows myosin to bind to actin and move it towards the center of the sarcomere. This is when ADP and phosphate are released and diffuse away from the complex. At rest, myosin is cocked and ready to grab actin and move it, kind of like a slingshot ready to fire. So as soon as the binding site is uncovered, myosin will grab actin and cause the movement. This moves the Z-line closer to the center of the sarcomere and shortens the myofilament. But this is only one step. If myosin took this single step and stopped, the sarcomere would shorten only a few nanometers and it wouldn't do us much good in the real world. For the muscle to really shorten, myosin has to take a lot of steps. It has to release the thin filament, cock itself again, grab actin, and repeat the movement. This process is called the cross-bridge cycle. It's driven by the energy stored in ATP and works like this. After myosin has taken its step, it's bound to actin and it won't let go. This is a rigor state. If someone is in rigor mortis after they die, it's because myosin is stuck to actin and won't let go. We can't move the muscles, they're completely stiff. Myosin needs ATP to let go of actin. If ATP is around, it binds to myosin, and myosin lets go of actin and uses the energy in ATP to cock itself. ADP and the inorganic phosphate are still bound to the myosin head. But then myosin can bind the thin filament again and take another step, releasing ADP and phosphate. This cycle repeats itself as long as calcium is around and there's ATP. All right, so now we've covered how a nerve impulse turns on the molecular motors that move us. The force generated by a single action potential is called a muscle twitch. A twitch lasts only a few milliseconds, so in the next video we'll talk about how a muscle can generate longer or stronger contractions.